Okay, in this last section in chapter 1, we're going to take a look at collecting sample data. How different ways that we can collect sample data and the issues that come that come about when you are going to collect samples a certain way. Again, before then, let's take a look at a proverb. A soft answer turns away wrath, but a harsh word stirs up anger. In other words, good sense makes one slow to anger, and it is his glory to overlook an offense is another proverb. But the idea is that if you do go sampling, make sure that you don't get on the wrong side of people. Just ask them the question. If they don't want to answer it, don't push them. And be a good statistician in that sense, okay? Again, just be humble about it, collect your data, and move right along. Here's the first thing. When we're designing an experiment, we need to decide whether we're, first of all, just surveying or experimenting or doing an experiment. And there's a difference between the two. For instance, in an experiment, you're going to identify your objective, collect sample data, and then use a random procedure that avoids bias, and then analyze the data and form the conclusions, okay? So there should be a procedure where you're going to take a sample that avoids bias, and that's kind of the main thing about this section. How do I avoid biases? The difference between an observational study and an experiment is that an observational study, you're just observing things, collecting tally points, for instance, or asking for a survey. Where in an experiment, there's actually treatments that are applied to experimental units. So what are you doing? That's the treatment. To who or what are you doing it? That's the experimental unit. And then there is a response variable. What happened? What's the effect? So that's what an experiment is. Whereas an observational study, again, you're not trying to manipulate anything. You're just gathering in information from the population. So examples are observational study. A poll is conducted which 500 people are asked whom they plan to vote for in an upcoming election. And then an experiment, for instance, would be to determine the effects of fertilizers. A farmer might divide 20 tomato plants into two groups. One received the fertilizer 1 and group 2 received the second fertilizer. All other factors for the two groups are kept the same, the sunlight, the water, etc. That would be an experiment. And in an experiment, we need to make sure we understand what the treatment experimental unit and the response variables are. So in this example, let's actually go through that. What are they? All the other factors of the two groups are kept the same. For the 20 tomato plants, group 1 has fertilizer 1, group 2 has fertilizer 2, and confounding does not occur. Confounding is very important. We'll talk about it in just a second. So experimental design, the treatment would be the application of the fertilizer. Experimental unit would be the 20 tomato plants. To who are you applying the fertilizer, right? And response variable, the growth of the plants. Well, did one fertilizer work better than the other or not? Now let's talk about confounding a little bit. Sometimes there are something's called lurking variables. A lurking variable is a variable that is not considered in the study but may affect the study. And that's what confounding is, when you have actually not accounted for a variable that have influenced your study. Confounding occurs in a study when lurking variables affect the outcome. Another way of thinking about this is confounding occurs when you are not able to distinguish among the effects of different fertilizers or of the different factors, right? In our case, it was fertilizer. So, for instance, if somebody put the tomato plants, didn't realize that they need sun, and in one case put some on the windowsill and the other underneath the stairs or something, then sunlight would be a lurking variable that produced confounding because it actually affected the growth of the plants, but was not considered in the study. The study was concerned about which fertilizer would work better, right? So that's what confounding is. Another example of confounding, flu shots are associated with lower risk of being hospitalized or dying from influenza. What are the possible lurking variables? Well, age, right? You can be hospitalized because of your age, health status, or mobility, for instance, seniors, right? There's different other variables that will affect you being hospitalized there, or dying from influenza, of course. So that's what confounding is. There's also something called a probability experiment. And in a probability experiment, we have the experiment, which is applying some treatment, the action. The event is the response. Observe its effects on the subjects. So very simple. Tossing a coin would be an experiment. And then the event would be observing a tail, right? Observe a tail. That's an experiment. And then the event. That is a probability experiment. We're looking at the probability of something happening. And we go through that event or that experiment and see that the event is that we're interested in is that we got a tails. Now please note this. No amount, and I like this quote, no amount of statistical torturing can salvage badly or poorly collected data. If a sample data are not collected in an appropriate way, the data may be so completely useless that no amount of statistical torturing can salvage them. So let's now talk about methods of sampling. The ideal one, and the one that we're going to assume for the rest of this class, is the random sampling. Right? This is the type that's discussed in this class for the remainder, for most of the exercises we're going to do. But I want to make sure that you're aware that there's other ways of sampling, namely systematic, convenience, stratified, and cluster sampling. Here we go. Random sampling. Members of the population are selected in such a way that each has an equal chance of being selected. Equal chance of being selected. If not, then the sample is biased. Right? So I will ask you later on a quiz or test the definition of random sampling, and these words, everybody has an equal chance of being selected, is important, or that there is no bias in the selection process, and that's a random sample. And that's what we want. How would you obtain a random sample of people in the US who suffered a stroke and were taken to a trauma hospital? Right? How would you obtain that sample? Think about that. Pause the video and think about that. Well, you would have to make a list of trauma hospitals in the US. CDC has a list of those. You can assign a sequential number to each trauma center, and then this would be called your sampling frame. The amount of hospitals, like 1, 2, 3, 4, 5, all those are numbers are assigned to a hospital. Figure out what your sample size is going to be. We're going to sample 200, 300, 1,000. And then use a random number generator, or just pull numbers out of a hat, right? And make sure that when you're going through this, then you are indeed either pulling out a hat randomly or using the random number generator. Now, please realize that random number generators also have algorithms, so they're not technically, theoretically, completely random. And note at the bottom here, this warning, that if you compromise in any of these, for instance, if you don't select all trauma centers, then you are introducing bias into the results. Okay, so this is just an example. There's other factors to consider to make sure that your sampling is random. Here is a steps to get a random sample using a TI-83 calculator. And please note that I will allow you to use your calculator. There'll be times when I have these slides where they'll say, here's how you use your calculator to get this, to do this or that. Please note that you will need to show some work, and the work usually is invoking a calculator function, right? In this case, random int will give you 1 to 30. That's what you choose. You can choose 1 to 50 or whatever the number is. And you're selecting 5 randomly selected numbers between the numbers 1 and 30. That's what the syntax says. And that's how you do this on a calculator, on a TI-83, 84 calculator specifically. Okay, so the other types of sampling methods are systematic sampling. So you're selecting a starting point and then selecting every kth element in the population. So every third in this case, or every fourth, whatever the number is. That's systematic sampling. There's a system to your sampling. There's something called convenience sampling, when you're lazy basically, and you don't sample everybody you're supposed to, but sample only those that you have easy access to. So doing this as in the picture, hey, do you believe in the death penalty, is not a good way of taking surveys, just shouting that outside of your window, right? There's also stratified sampling, where you take your population, subdivide into at least two different groups, and then those two groups usually share some kind of characteristics. Then draw a sample from each group, or a stratum. So this here is an example. Your population may be divided into men and women, for instance, right? And then in the women, you would select some of them, and in the men, you'd select some of them, right? This is called a stratum, and this is called a stratum. Women being the category or subgroup of your population. So stratified sampling. You notice that there is a slight difference, but there is a difference between stratified sampling and cluster sampling. Cluster sampling is when you take your population and divide it again into clusters or sections. But then the key difference here is that in the sections that you decide, all of the members in those sections get to be surveyed, okay? All of them. So whereas over here you decided to choose only some of the women and some of the men in the stratified sampling, once you've separated them into those categories. When you separate in cluster sampling into categories, you would take some of those categories, but you will survey everybody. And the idea of surveying everybody, usually cluster sampling, is pretty good because you get a representative sample of your population. Right, when you take the entire cluster and you don't survey some, but you survey everybody in that cluster. So that's cluster sampling. So there's random sampling, systematic, stratified, convenience, stratified, and cluster sampling. Those are the different sampling types. Now let's talk about errors in sampling. There are different types of errors that can occur. Sampling error will always occur. And that's just telling you that there is a difference between what you got in the sample results, and what the population results would be. Such an error results from chance sample fluctuations. We will always have sampling error. Why? Sampling error is basically the difference between the information gathered in the sample and information that you would have gotten if you had surveyed the entire population. So there's always going to be a difference. Sometimes it's very small difference, sometimes it's very big difference between what you got in the sample and what you would have gotten in the population. Please note that sometimes you're not able to survey the entire population, and that's why you're surveying a sample. So sampling error will always happen. It's just the name of the game to statistics because you're sampling or taking information from a sample. What we do have control over is non-sampling error. Non-sampling error, sample data that are incorrectly collected, recorded, or analyzed, such as by selecting a biased sample, using a defective instrument, or copying the data incorrectly. We want to minimize that. These are human errors. Non-sampling error are human errors, and we want to avoid those and control those. So make sure you're selecting without bias. Make sure you don't have defective instruments in your survey process, and you copy and paste everything correctly. So here's some examples to go along with that. A recent poll showed potential voters favored the proposition 52% to 48%. The margin of error for the poll is 3%. So this represents a sample, right, of the voters who favored the proposition 52% to 48%. But you're also given this information, the 3%. That is the margin of error. So it could be 52 plus or minus 3%. 48 plus or minus 3%. Okay? Non-sampling error example here. During the presidential election of 2000, if you guys remember, early results from Florida exit poll were skewed by a programming error. I think there was something to do with the machines, right? And so that's non-sampling error. That could be fixed. That could have not happened. And it's because of the machines that allowed this error, right? So I think it was the Bush election, the time that Bush won, if I'm not mistaken though. So there's that difference. Sampling error always happen. Non-sampling error doesn't necessarily need to happen, and we want it not to happen because it's error that is controllable, that we can control. Okay, let's talk about more about collecting data. Let's talk about collecting data when you are designing experiments. The idea in an experiment is you want to make sure there's a randomization. So subjects are assigned to different groups through a process of random selection. Right? In an experiment, we have patients There's a treatment group and a control group, somebody that just gets candy and somebody that gets actually the medication. And then you do a follow-up with each of these groups and see what the difference is, right? And compare the results. So you have a random selection process during this entire setup. You also want replication in your experiments. So your experiment should be repeatable. Repeat the experiment on one or more of the subjects or groups. So you should be able to do that. And then it's best to have a blind, or even better, a double-blind experiments. Blinding means that the subject doesn't know if they're given the treatment or a placebo, right? Whether you were given a piece of candy or you're actually given the pill. Double-blind means that the doctor doesn't know either. They're studying you, and they are looking at the symptoms, the results after you've been taking the medication or the pill. They don't know which one it is, and they're actually writing down their conclusions, right? And I was on a plane once. I remember this is, I will never forget this, because it was a lady, a pharmaceutical representative, that shared with me how crazy faith and hope work. And we know that, or we call that as the placebo, right? She said no matter what study you look at, every single time the placebo effect, people think that they're getting the pill when they're not. Even in cancer patients, their health is on par with those that are getting the medication until they realize that nothing's changing, right? Their health is on par until they realize, look, nothing's getting better, so I'm going to give up. And once they give up, then they go downhill in terms of their the health, even worse. Placebo effect's pretty strong. Okay, some more observational vocabulary, observational studies. So we looked at experiments just now. Now let's talk about observational studies. We have something called a cross-sectional study. In a cross-sectional study, data are observed from one point in time, right? Retrospective studies, data are collected from past observations, usually called case control studies. And then we have prospective studies, data are collected in the future from groups sharing common factors, sometimes called cohorts. And this is usually called a longitudinal or cohort study. So there's different ways that we classify observational studies. From one point in time, from the past observations, and then from future time. And there's examples here for each one of these. So for instance, you want to study students who were in math boot camp and who were not, right? That would be called a cross-sectional study. Studying a group of drivers who died in car crashes and another group who did not die in car crashes. So you would have to take a look at in the past and say, okay, these people died and these people did not. And then a prospective study would be taking a look in the future. So you're studying a group of drivers who use cell phones and a group of drivers who don't, and then see who ends up dead and who doesn't. How many were in the accident, right? That would be you taking a look at the result in the future. So there's different types of observational studies as well, namely cross-sectional, retrospective, and prospective. And the prefixes sort of give it to you. Cross-sectional, this is hyphenated, so you're taking a look at two, right? People, see how they're doing before, see how they're doing after. A cross-sectional, or sorry, retrospectual, retro, right, before or in the past. And then prospective, that word is associate, or you can associate that with the future. Okay, in the next chapter, we're going to take a look about summarizing and graphing data, taking a look at representing data in different ways. So make sure that in chapter 1, you have your statistical thinking cap on, and you understand how incredibly important it is to think critically about how information is presented to you, right? And that you, as a researcher in the future, would need to gather information in an unbiased way and present it also in an unbiased way. Hope this helps. Let me know if you guys have any questions in the homework and lectures discussion module item.